Hey everyone, and welcome back. Today we're jumping into a really cool programming concept called tail recursion. It's one of those techniques that can make your code feel super elegant, but as we're about to see, it can also make it incredibly efficient. But first, let me ask you a question. Have you ever written a recursive function, felt all clever about it, you run it with a kind of big input, and then, boom, your whole program just dies a fiery death?
Yeah, of course you have. We've all been there. It's the infamous Stack Overflow error. It's like this hidden danger that's always lurking behind recursion, and it is the exact problem we're going to solve today by learning a much smarter way to write these functions. So here's the game plan. We'll start by looking at the recursion trap itself, then introduce a smarter way to do things. We'll see the compiler's awesome magic trick that makes it all possible, learn the practical pattern for how to actually write it, check the fine print to see where it even works, and finally, we'll talk about why this whole concept really matters.
Okay, let's get right into it. First up, the recursion trap. Let's break down why our normal, everyday approach to recursion can be an absolute memory monster.
So on the left, you've got your classic recursive factorial function. Now, think about it. To solve fact 5, it first needs the answer to fact 4. It can't finish its job yet, right? The multiplication has to wait. So it has to pause and put its unfinished task, that little multiply by 5 job, onto a to-do list in memory called the call stack.
And this just causes a chain reaction. Fact 4 does the exact same thing, waiting for fact 3, which waits for fact 2, and so on. Each function call just piles another piece of unfinished business onto this memory stack, just waiting for the one below it to finally give it an answer. If that input number is big enough, that stack of unfinished work just grows and grows and grows until it runs out of its dedicated space in memory, and bam, stack overflow. Your program crashes. Hard.
So how do we get around this? Well, we embrace a smarter kind of recursion. The main idea here is to flip the whole process around. You finish your work before you pass it on. And this is what we call tail recursion. The definition is actually beautiful in its simplicity. It just means a recursive call is the absolute, final, last thing a function does. There's no pending multiplication, no and then add this later, no other operations just sitting around waiting. The work is already done.
Take a look at this simple print down example. The function does its one job, it prints a number, and then it calls itself. Once that recursive call is made, the current function is completely finished. It has literally no reason to stick around and take up memory.
Now, this one simple change unlocks a massive superpower. But here's the thing. It's not from us. It's from the compiler. This is the real magic trick, something called tail call optimization.
So, tail call optimization, or TCO, is when a compiler is smart enough to see a tail recursive call and basically say, hey, wait a second, this function is totally done. There's no more work to do. I don't need to save its state and create a whole new memory block for the next call. I can just reuse the exact same memory space. Under the hood, it basically turns our elegant recursion into a hyper-efficient loop.
And the difference this makes is just staggering. On the left, a standard recursion's memory usage grows linearly with the input. That's O of n space complexity. But look at the right. With tail recursion and TCO, the stack size stays completely flat. It's what we call constant, O of 1 space, which is just as efficient as a simple while loop. It's the best of both worlds.
This quote from Geeks for Geeks really nails it. The compiler can avoid making a new stack frame by simply sending control back to the beginning. So it's not really a function call in the traditional sense, it's more like a simple goto or a jump.
Okay, so the theory is great, but how do we actually write code this way? Well, this brings us to the most practical part of our explainer, the accumulator pattern. The real secret to making this work is something called an accumulator. And it's really just a fancy name for an extra parameter you add to your function. Its whole job is to hold the results so far, carrying the completed work forward into each call, instead of calculating everything on the way back up.
Let's look at our factorial function again, but this time, transformed. On the left, the old way. On the right, the tail recursive version has a new parameter, ACK. Now, pay close attention to where the multiplication happens. It's not hanging out after the call anymore. It's happening inside the arguments for the next call. We pre-calculate the next value and just pass it on.
So the whole idea is to use that extra argument to accumulate the result as you go. Then, when you finally hit your base case, when n gets to 0, you don't return some starting value like 1, you return the final answer that you've been carefully building up in the accumulator all along. Now, it's time for the critical reality check. All of this magic hinges on the compiler actually doing its job. So let's have a look at the fine print.
This is the question every single developer watching this is probably asking right now. That's cool and all, but does my language actually support tail call optimization?
And the answer is, it's complicated. For functional languages like Scheme and Haskell, absolutely. Yes, it's guaranteed. It's a core feature. For C and C++, yeah, usually, especially if you turn on the optimization flags. But, and this is a big one, for languages like Java and Python, the answer is no. They explicitly do not support TCO. So even the most perfectly written tail recursive function will still build up the stack and eventually overflow.
So, with all that in mind, you might be wondering why this matters, especially if your language doesn't support it. Let's tie it all together and talk about the big picture.
Here's the bottom line. In languages that support it, TCO lets you solve huge problems recursively without any fear of stack overflows. You get constant O of 1 memory usage. But even where it's not supported, learning this concept is incredibly valuable because it teaches you a new mental model. It forces you to shift your thinking from, I'll do the work on the way back, to, I'll do the work now and pass the complete result forward.
And really, that's the thought I want to leave you with. This isn't just a technical optimization. It's a different way to think about solving problems. So ask yourself, what problems could you solve differently, maybe even more elegantly, by passing the answer forward instead of waiting for it to come back?